So first up is Alan Cudmore, who's going to do the CFS platforms. And he's got the whole abstraction layer and take the agenda as a guidance. So he's had freedom to, based on this morning's discussions and things, reprioritizing the order and things like that. All right, here's Alan.
Let's see here. Hi, my name's Alan Cudmore. I work at Goddard Space Flight Center. And I did a lot of the original work on the OS abstraction layer and the original CFE core. And the first thing I want to talk about is the CFS platforms and how a little bit of history about the OSAL and the PSP, sort of how they became what they are now, and some ideas for future work. So I wanted to talk about just a little bit about the history of the OSAL and PSP, sort of my world's view of what a device driver is, and talk about some potentials for future PSP device interfaces and sort of how to manage the complexity with these type of abstraction libraries. And then, other PSP needs that we definitely have to get in there. So originally, the operating system, well, first of all, what is the operating system abstraction layer? It's a small software library that isolates an application from a supported real-time OS and other OSs such as Linux. With it, we're able to have our core flight system and core flight executive compiled for different operating systems without modifying the source. So this is not a dynamic abstraction, it's a compile time abstraction. For example, if you call OS task create in our software, if you're compiled for VxWorks, it'll call task spawn. If you're compiled for RTEMS, it'll call the two RTEMS functions to create and start a task. And likewise on POSIX OS, it'll call pthread create. And currently the OSAL is a standalone project and it doesn't require the CFE, although the CFE is dependent on the OSAL. So that we actually even have a project at Goddard that uses the OSAL that doesn't use the CFE. Now the platform support package, it's a software library that adapts the CFE core and the CFS applications to a specific hardware platform and operating system pair. It was derived from the early version of the OSAL, where we had a little BSP layer with startup code and make rules and things like that in the OSAL. In fact, they still are kind of in there. And we had a hardware abstraction layer directory in the OSAL. We called it the PSP so we could avoid confusion with something like an RTEMS or VxWorks BSP. It was kind of hard to convey to management when you're talking about two different types of BSP. And currently, the PSP covers just the minimum amount of APIs required to get the CFS running on a platform, on a processor board and OS. And it's currently, fairly specific for the, it's tied to the CFE, CFS. A little bit about how these two libraries got to be where they are now. The first version of the OSAL we used for the SDO mission. We had a RAD 750, or we have a RAD 750 running VxWorks, and we have a number of Coldfire processors running RTEMS, and we wanted to be able to have generic flight software, our core software. So we created this OS abstraction layer. Now originally, the OS abstraction layer had this little hardware abstraction layer in it, and it had all the build rules, and it had some startup code, and it had memory access functions and things like that. And as we developed the CFE, we would get requests for new users, and they would say, well, can you develop or release a new version of the OSAL to support my board? And to us, from a CM point of view, it really didn't make a lot of sense, because we had, it's like, do we want to release OSAL version 3 because we have a new processor card? It just didn't makes sense. So we decided to split the OS and split the hardware-specific and platform-specific parts of the OSAL off into the PSP. And so now the purpose of the OSAL is just to cover the operating system interfaces. And as a result, it's been much more stable and had much less changes than before. And the PSP became the glue logic that ties the CFE and CFS to a particular platform and OS. So before I get into the next section, because I guess as we're going along, we do just have the minimal support for abstracting hardware in the PSP for the CFE core and some of the CFS apps, but not all of them. And so, a logical question is, why don't we support, device XYZ on the PSP? And it usually comes down to, how many drivers we want to have in the PSP and how we deal with all those. So before I get into that, I'll talk about my view of a driver. A driver can take a few different forms. The simplest is when you have just a small microcontroller-based system with very low-level software. It can just be some simple functions that say, read from this I2C bus or something, or send an I2C message. It's not really written with any standard in mind, but the CubeSat that I'm working on kind of has firmware that has a bunch of these functions. In fact, I don't think the firmware on my CubeSat project has any sort of standard POSIX-like functions for the device I/O. And then, of course, we have the whole world of Unix device drivers. And in the Unix world, POSIX kernel, the drivers are in kernel space, and the user code interacts through a standard open, close, read, write, I/O control API. And it makes a nice, clean interface, but we don't always have the ability to have that sort of model. And of course, there are some operating systems like RTEMS and VxWorks that they do support that open, close, read, write API, even though there isn't a user and kernel space barrier. It's just there for consistency and compatibility. And that's always an option for what we want to do. Oops, did I go backwards? Oh, okay. So, as such, I probably covered a lot of this already, but the current PSP interfaces include startup, whoops, hit the wrong button here. Startup and restart. Where am I? Here we go. Startup and restart APIs. So we need to define how we start the CFE and how we restart the board if the CFE wants or needs to have an exception-based reset. How do we log exceptions, things like that. We have memory access APIs. How do we deal with EEPROM or other non-volatile memory? How do we, if there's special procedures to write with pages and verify the data that was written. Sometimes we need special access for RAM. We've used processor boards before that didn't have byte writable RAM, so we had to be able to do read, modify, write. And that's where our cloned memcopy utilities come in. So sometimes, you'll see in the PSP we have our own memcopy function, which on most platforms it just is a straight wrapper around the standard C memcopy, but it's there just in case you need something. If you have a special memory interface or you need to turn on a memory or switch a bank or something before you do one of these calls. And then we have some device I/O APIs for the type of processors that do I/O, different based I/O, not memory mapped I/O. And then we use it to store the compiler definitions and switches, although that's kind of changing based on Joe's call when he was talking about the CMake stuff earlier today. That's an effort to not have to have a lot of these switches kind of buried down in the PSP.
So, Alan, before you go on that, I thought that maybe 3 or 4 weeks. Sorry. Yeah. I thought maybe 3 or 4 weeks ago at one of the CCDs, CCB meetings, we talked about the memcopy, memset PSP functions and felt that there was no rationale for it. So we were saying go back to, oh, we changed our mind? I'm cool with it.
It's still an action.
Yeah.
Okay, so it's in discussion. Okay.
Because we wanted to ask Alan about it.
Ah, yes,
And I
thank
think,
you.
You know,
Yes,
and this,
okay.
and this is the reason why we
Yeah.
might need something like that. Now, you know, it seems like we should be able to get by without ever using something like that, but, you know, I guess we can go after the hardware designers if we ever can't use the standard utilities. But, you know, if we're spending most of our time just using standard platforms and Linux and things like that, then they definitely aren't needed. And it just seems like it's extra code. But I've definitely used projects that have needed them. Okay, so when we talk about adding new device support and abstracting new hardware for the PSP and for the CFE and CFS in general, one of the problems, at least in my mind, that I keep thinking about is, you know, how can we keep expanding the APIs for the PSP and be able to possibly support it all? You know, it's like, for example, do we want Bob Super GPS and gyro module in the PSP API if only one user with one board is ever going to use it? You know, we just can't have, like say, okay, now every PSP we have is going to be ported to support this new interface if nobody's ever going to use it, and all the implementations other than one are just kind of like stubbed out or not used. So we have to kind of figure out a smart way to allow the abstraction to grow but still be able to manage it. Part of it is a management problem and a resource problem. You know, ideally we would just have the PSP grow to support all the hardware we would ever need, but we have to maintain it and we have to have a lab that we can test all this stuff too. So there's a couple of options that I thought of, and one of them I used on the CubeSat that I'm working on now, a CFS mission-based hardware library. We also use that on our MMS mission. And another is the development of a PSP device plugin model, or probably what would work the best is just a hybrid model where we could use either one of these. Talking about a mission hardware library, the CubeSat I'm working on, it uses a very small COTS CubeSat board, this CommSpace NanoMind, and it's running FreeRTOS. And we wrote a minimal PSP for it and just a real basic OSAL port. And all of the mission hardware is abstracted through our mission hardware library. A lot of the functionality that CommSpace delivered with the board is in their firmware. So we have a bunch of I2C functions, SPI, and they support the UARTs and DMA and interrupts and everything. So it's really nice what they provided, and it's all integrated with the OS. And so, and one of the things we wanted to do in this mission, not only is get up to speed as quickly as we could, because it's a very low budget mission, but we wanted to be able to simulate all of this hardware and talk to a dynamic simulator. So we ended up just putting all the mission-specific hardware libraries in the CFS library, and all of our mission apps just talk to that. For example, we have gyro, GPS, sun sensors, magnetometers, torquers, and things like that. And so when we're running, and we actually have two versions of this library, one's for the embedded ARM target running FreeRTOS, and the other's for Linux. And when we're running on Linux, we can actually just simulate as much or little of the hardware as we want. And we can also talk to our dynamic simulator. I can even run it like on my laptop. I have a simulation where I can run the whole suite of the CubeSat software and have it interact with this 42 dynamic simulator. And you can see the thing, you can send the command to tell it to go to charging mode, and the satellite will reorient itself until it's sun pointing. So it's actually, it worked out really well for us. And on the target hardware, this library talks to all the actual devices on the board. And so everything up here in the app level, and of course all of this stuff too, doesn't change. It all stays the same. So our ACS app doesn't really have any conditional code in it anymore. It just all talks to this library. And so that's one option. And I guess probably not going to read all this because I said most of it. I guess another thing about the APIs is we were able to create tasks when we need them, like the Linux version of this. When it talks to the simulator, it has to spawn an OSAL task for the communication. And it can use all the underlying APIs if it needs to. And it's pretty easy to talk to a simulator at that level. The cons are that model kind of breaks our layering by having hardware-specific code at the app layer. And that's not ideal, but sometimes it's necessary, and especially for kind of a one-off type of mission that we're talking about. And we also have to have an implementation for each platform in OS. Like in our project, we have one for the NanoMind running FreeRTOS and one for Linux running on a PC or Raspberry Pi or whatever. I already talked about that. And so another idea, which this doesn't actually exist, at least at Goddard, I'm not sure if anybody else has worked on this, but the idea of creating PSP plugins for devices. And so here we would have a model where you could create a plugin that could, we would have to create some sort of API to install and query the plugin interface so that we could add a new driver if we need to. And we could create some sort of generic device API to be able to do this. And that way, a mission could add as many plugins as they need for devices without really placing the burden on the PSP itself and the project. The PSP continues to be as small and generic as possible, and thus easier to maintain and distribute to a wider number of users. And the users could write plugins as needed, and of course plugins would hopefully be compatible for different platforms. Again, I probably said most of that. And then we could have a hybrid approach too, which I think makes sense, where some of the lower level devices we might want to create a plugin and platform support package. But I also think it makes a lot of sense to be able to put mission-specific hardware access functions in a CFS library. And ideally we would abstract everything, but I think just from a resource point of view and being able to debug and port, it just makes sense. It just makes things easier. And so with this hybrid approach, we could use PSP device plugins. We could use the CFS mission hardware libraries. And I think we could also include some specific libraries that we might start factoring out some of the common code, like common sensor libraries. As I'm starting to work with this CubeSat that I've been working on, been trying to isolate some of these interfaces, like for GPS and gyro data and accelerometer data and things like that. And I think it makes sense of, more work a lot with these little Raspberry Pis and Arduinos, and I'm starting to see some of the open source libraries available for them, and I think it makes sense to have some sort of common sensor library. And I was even thinking about some sort of sensor bus architecture that could plug into the whole CFE architecture, where we could subscribe to sensor data from different sources and have sensors coming from simulators, coming from an Arduino with the sensor connected to it over the network, or just coming from an actual device on a board. And that way, it could be very flexible about bringing up new hardware and testing it for a mission. And then, the flight code, ACS or whatever applications we have running on there can be generic, and it can just subscribe to the best available data that it can get. And I think that's it for that one. Is there any?
Actually, I have a quick question.
Mhm.
And it's kind of for you and the group, if anybody's, I mean, and actually, you might have worked, Jonathan might have worked at, pointing at Jonathan. So, I mean, your plug-in, your hybrid approach, really, if you pushed it up a layer to the application layer, command and telemetry packet, there you could have a standard definition, which I guess is like the space object SWAS.
You mean like a plug-in
So-
at the CFS application
At
layer?
the application layer, and then it's regardless, I guess, of the, you could still merge either of your models, I think.
Mhm.
I'm just kind
So
of throwing
one,
out.
one thing, I guess I'll point through, a model that JSE had used is, there's a plug-in, so if there's a star tracker, there's a corresponding CFS component that goes with that star tracker. So when they plug in that star tracker, they plug in the CFS app that goes with it. Idea for that given piece of hardware, there's only, you only have to develop the software once.
Okay.
Well, so that's almost true.
Almost, right.
It's almost true, except that like, let's say, I know the example you're talking about, sorry. Like, so the example I can give, you're absolutely right. When we do an app, we have like 10, 15 mission apps, each one for every sensor has an app. And that works, except when you go between operating systems, like VxWorks, you have to do a memory map to whatever card to get to the data. And if you do Linux, then we do an ifdef to get to whatever, or an ifdef to get to the sim, which is okay. We sort of managed it with ifdefs in those apps,
Mhm.
and that worked fine. I'm not going to complain about it.
CCSDS has your solution.
Okay, so, but I like that. I think the apps work well. The thing is, and so if somebody else has that same IMU, you can give them that app, and I think it would be very little changes if they had a different platform, is the point. Because it does talk everything that that device knows.
And that's at the application, on the software bus.
And it's,
So
yeah,
as
so
opposed
one
to a-
end of it, it's on the software bus, the other end, it talks directly to the hardware.
Yeah, so I want to
Okay.
Yeah.
So-
go up a couple slides. And that one will work.
This one?
The one with the green stuff. So what CCSDS has is those plugins, like there's a packet service
Here.
and a memory access service that are common interfaces. Because underneath, they're all like attached somehow. There's some underlying, either 5053, there's SpaceWire, there's direct memory. So you put your changes in at that layer, your memory access service or your packet service, and the app at the top talk those services.
Mhm.
So there is across the top there, just below the app bubbles, there's an abstraction.
Okay.
It's sort of like your POSIX kind of abstraction. There's a send, there's a receive, or whatever.
Mhm.
So I think that's sort of your hybrid. You still have to write, some special I2C driver if that's what your hardware has. But the apps don't need to know that. All they knew, I got to send a packet or I got to do memory access, kind of thing.
Okay.
So there are, though not the only group I know that's implemented that are the Chinese,
Mhm.
which is, and they all thought this was the greatest thing ever. So it does work.
Yeah, so I think for example, I was thinking about creating this sensor bus library that could plug in all these nice little open source or common sensors and be able to simulate them as well. Maybe that would be the type of interface we would want to use rather than just making something up, having a service based on that standard.
So, real quick, guys, now looking at real time for SPN, I'm thinking there may be some commonality in issues in implementing sensor applications and interactions and devices that we may want to come up with some general model for, because the SPN, every network connection is basically a sensor, or transmitter receiver. But but we're I'm going to run into those real-time issues that may apply in this environment as well that maybe we should be all thinking about.
Okay, yeah, that's great.
So join Alan's PSP group.
And it's kind of looking at it the different direction also, is when you said, so in favor of the plug-in,
Mhm.
where you were saying you're starting to see commonalities between all these different sensors.
Mhm.
If you can somehow classify them, and it's still something I haven't been able to do, you know, this is the, in the C++ world, you know, these are the base class methods for an actuator or something. Once you do that, it's the one thing you haven't mentioned is what if I've got an architecture, but all of a sudden I want to go to a different sensor?
Mhm.
So it's not even a different mission. I just want to pull this sensor out and I want to put a new one in. If you've built to that common API, then all you have to do is replace that driver
Right.
and none of the stuff above it. And so that's why the plugins work well.
So that's one of the things S-Tech has done, the European Space Agency Technology Center is done with the EDS. And so they actually auto-generate those device interfaces from an EDS kind of thing. And so they're solving it in a different way. So they don't even worry that there's an abstraction there. They just auto-generate it for that new sensor or that new device. But having the concept of having some abstraction there that you can auto-generate to, or your framework, is important. So
Yeah,
what we
it'd
were
be
saying when we were talking about it at lunch, you need something some defined abstraction to be able to generate code to. In this case, it'd be the CFS abstraction or whatever you end up calling it.
Yeah, so it sounds like there's a common theme here, and it's, you know, and it.
May I comment on that?
Yes.
Since this source is actually here, I can sort of argue for UK Space Agency. Thank you for bringing that in, however. It's correct that we auto-generate, that the plan is that we should auto-generate the drivers based on EDS. However, it fits into an overall architecture, which is not really visible here. So that's why you come up, I can see that you have different approaches, but because you don't have an overall, what we call an overall avionics architecture, so where your different application fits in. So I mean, I can ask the question, how does this architecture manage a sort of FDIR? So how can you actually switch between different sensors? Where is that decision coming in? Where do we have the AUCS, the control loops? How do you actually manage the frequency of the readout of the sensors? So that's the overlaying avionics architecture that the drivers fits into. So yes,
Okay.
we have a solution, but the solution is supported by an architecture.
Okay. So I think like some of the points I was trying to get across are, you know, it just sounds like there's a lot of common themes for being able to manage the growth in the PSPs and being able to figure out how to deal with new mission hardware and sensors and things like that and new libraries. So I think it's obvious that we probably need to form some sort of working group to get this stuff together in a manner that makes sense and, you know, is reusable as much for everybody. You know, we want to promote as much reuse as possible, and from our perspective, we want to make this work on you know, the smallest CubeSats up to the bigger missions. And I guess another thing that I didn't mention, it was in the agenda, I guess, was also in the PSP, I think we definitely need some additions to just what we have now. It would be nice if we had more of a porting guide and supporting documentation for the PSPs and a test suite. It'd be nice if we could, you know, once you follow the porting guide and port a new PSP to your platform, that you could actually run the verification suite and know that it's working and will support the CFS. Okay, so, you know, feel free to contact me and any kind of ideas or about this topic, and we can definitely work on it.